So welcome back, everybody. The topic today is to go into more details of the Boltzmann machines, and Boltzmann machines applied to the quantum mechanical problem. Now, one of the things I want to revisit is the theory, the more traditional theory for Boltzmann machines, and why that is interesting as well. Now, last week, we discussed the benefits of dealing with Boltzmann machines, and Boltzmann machines are so-called generative models. So that means, and as we discussed last time, generative models, they are meant based on a probability distribution. So this is actually very interesting for us as physicists. They are meant to represent some kind of data. So you could train a probability distribution to generate examples of cats and dogs based on the training of images of cats and dogs. So it's not that you have a convolutional neural network, which is used to train and reproduce data, but now you have something which can generate new data. So that's the big difference. So when you have a probability distribution, which you have trained on a data set, the whole idea then is that you can use this probability distribution to generate new data. Now, what I wanted to do today is, one, to step you through some of the basic ingredients with Boltzmann machines, but this is something which will not be that relevant for quantum mechanical problems, because when it comes to quantum mechanical problems, we are going to go back to what we did in project one, and we are going to use the standard energy as our training function, the function which we want to optimize with respect to a given set of parameters. Now, when you use Boltzmann machines in deep learning, so these are a kind of basic starting points for what is called deep generative models. These Boltzmann machines are normally easy to train, but they involve the calculation of a partition function. So what I will be doing now is to give you the basic elements for setting up a Boltzmann machine for a deep generative neural network, normally what we call deep generative learning. But then for our own practical purposes, we are going to train these probability distributions in order to optimize the energy. So as I mentioned last time, for us, when we are setting up the problem now, we are going to basically reuse project number one. So we can use everything we developed there, the Monte Carlo Markov chain with the metropolis sampling. If you wish to change the Gibbs sampling, which is much used in these deep generative models, then we would also reuse our importance sampling. We're going to reuse our blocking method. The only thing which is going to change, as we mentioned last time, is the type of wave function which we're going to use. So I want to bring up these distinctions and also try to emphasize why generative models are so interesting. A lot of the new activities in deep learning actually rotate around generative models and unsupervised learning. So if you look at the very popular software for generating images like DALL-E, D-A-L-L-E, which probably many of you have tried, this is based on generative models. And the Boltzmann machines are one of the possible approaches. Now, the reason why we focus on them is that they have a very strong link with what we are familiar with from physics. And at the same time, they allow us, from a pedagogical point of view, a very easy link or a pretty simple link between what we did in project one when we set up the variational Monte Carlo machinery and had a trial wave function. Now, when we are going now to simulate the system, it's the optimization of the local energy, which we are, or the expectation value of the local energy, which we are going to look at. Then, when we're done with that, so most of the day today will focus around the mathematics of Boltzmann machines applied to the quantum mechanical problem, and also standard Boltzmann machines. And after we're done with that, we start to look at the calculations involved with standard neural networks, if somebody wants to apply that. That will be discussed in more detail next week. And if you now look at the final schedule for the semester here, if you take a look at the official website of the University of Oslo for Physics 4411, if you scroll down here, you will see now that today we are mainly going to focus on the Boltzmann machines and how we can implement these in project number 2. And then we have the last, lecture is going to focus more on neural networks. And then we have the last session where we're going to summarize and just keep working on the project. And then the remaining sessions in the month of May will mainly be devoted to work on project number 2. And then we have the final deadline of May 31. I would also like to mention to you the textbook, which I normally recommend when it comes to studies of deep generative models. And that's a textbook by Goodfellow, Benjo, and Co-Will. And you find that one here, and you can download every chapter for free. So I'm going to put this link into the chat here, so you can download these different chapters later. And in our case, it's essentially chapter 18, and you can look at chapter 16 as well. And Monte Carlo method is something which we have already covered. And then you have the chapter 20 here, which deals with deep generative models. And Boltzmann machines are one of the type of models which are used. And they form often the basis for many of these approaches. Now, in our case, today we are going to now look a little bit more at both Boltzmann machines with quantum mechanics and without quantum mechanics. So let me switch over to the whiteboard, because we will basically stay with the whiteboard for the rest of the day. Any questions so far about practicalities? I'm going to repeat many of these motivation arguments for why we deal with Boltzmann machines. So there's a very important issue for us, and that's the pedagogical issue, because it allows us to link directly with what we have in project number 1. And as I said, these deep generative models, they're really at the forefront of research in artificial intelligence and machine learning, in particular since we're dealing with unsupervised models. And it also links well with a statistical interpretation and what is normally called Bayesian statistics. But let's bring up some of the basic points here of what is going to come here. So if you look at Boltzmann machines, and I'm going to use the acronym BM, these are part of a huge community of research which deals with what we normally call deep generative models. And these models, what they typically do then is to optimize a probability distribution. And I'm going to write this probability distribution as a function of some variable x. So x, in our case, is going to be the input variable to the wave function. And they're going to depend on some parameters theta. So what we want is to, and this is the difference between what is going to come now. So we are going to often, when we deal with these models, is that we want to maximize the probability. And in this case, we are going to find an optimal parameter or set of parameters theta, given a set of parameters theta. So theta hat refers to the optimized parameters. And instead of optimizing the probability distribution, so we want to maximize the probability distribution. So clearly, when you create a model for probability, you don't want to have a model which minimizes the probability. That is counterproductive. You want to have a model which maximizes the probability. Now, often the probability distribution is written in terms of exponentials. which means that since you have a probability distribution which is written in terms of exponentials, it's often from a computational point of view much easier to actually calculate or optimize the log of the probability distribution. So this is a probability distribution X, P of X, as a function of these arguments theta. So this is a huge research field, and it's focused on unsupervised learning. So if you think of something like convolutional neural networks, which are widely used in imaging, these are methods which require labeled data. So that means that you would feed into a deep learning model millions and millions of images. And then you want to train a network so that you can actually recognize these images as dogs or cats or whatever. When you're dealing with generative models, you're training a network not to classify pictures, but actually to be able to generate new images of cats and dogs, just as an example. So in physics, we are very much interested in this approach in order to find a probability distribution so that we can generate new events. So this could be events for an experiment at CERN, just to give an example, or it could be events which are needed in order to label whether you have an ordered or disordered phase. If you're looking at the phase transition type models, spin type models like the Ising model or the Heisenberg model or similar models. So I want you to keep this kind of distinction here between the deep generative models, which are typically represented by these Boltzmann machines. And when we look at a Boltzmann machine, that is something which takes into account the Boltzmann distribution. And normally we are going to deal with something which is called a restricted Boltzmann machine. But in general, this probability distribution is going to be given by a function which now contains another function of x of theta. And this is divided by the partition function, z of theta. Now, this probability distribution, when we think in terms of continuous variables, is going to be given by p of x of theta. That will be given now by an integral over dh, and h are now the so-called hidden variables, which will be represented by hidden layer. And you can think of these as variables which are being used to give you additional freedom to parameterize this probability distribution. And the typical function is then given by some temperature, and then there is an energy here, which depends on energy function, which now depends on these parameters theta. And we are coming back to this. And this is divided by the partition function, which is nothing but a normalization constant. So the partition function then is defined as the integral over d of h and the integral over d of x. And then we have the z to the minus p no beta of e of x of h and theta. And this is about a function which now depends only on the unknown parameters theta, which are the parameters we want to use in the optimization. So in the optimization process of this specific standard setup of a deep degenerative model, what we normally end up doing then is to implement some kind of Markov chain Monte Carlo approach. So compared with the standard neural networks, and this is one of the pedagogical reasons why we have implemented project number 2 using Boltzmann machines, is that we don't use the back propagation algorithm with automatic differentiation and so on, which is common to a standard neural network. So that means that the optimization here requires us, so the optimization involves the calculation of the gradient. So this is early in the morning for me, guys, whereas you are in the early afternoon here. The optimization involves then the calculation of the gradients of delta phi, and then of this log of the probability distribution as a function of x. Now, the full probability distribution is actually given by this p of x of h as a function of theta, and that's given by e to the minus beta of e of x, a function of h, and we're going to define this function just in some few moments, and z of theta. That is the full probability distribution. But normally we define something which is called the marginal probability. And this marginal probability, this p of x of theta, is now given by the integral over d of h. So we are integrating away all the variables h, so that we have only a probability distribution in terms of the x and the unknown parameters theta. Similarly, we can also, so we should actually write probabilities here. Probabilities. And these are the quantities which we are going to calculate now in the implementation of the Boltzmann machine for quantum mechanical system. We will also need this one, because when we are going to look at how the hidden layer behaves, we need a probability of the hidden layer as a function of this hidden variable h. And this is going to be given as a function of a d of x of p of x h. So this is a new integral. And if these are discrete functions, this will obviously be either a sum over h of p of x of h of theta, or if we are interested in the probability of h, this is going to be a sum over x of p of x of h of theta. So this is in case we are dealing with discrete variables. If we have a continuous variable, we are going to have to integrate over all the h's. In practical implementations, we are essentially going to deal with a mix of both continuous variables and discrete variables. So a naive algorithm here is very similar to the way which we have been doing the Monte Carlo calculation for in project number 1. So if we now look at the algorithm for this, so this is a standard Monte Carlo Markov chain approach, as you have seen in project number 1. And that's why these methods are so interesting for us, because they allow us to think in much of the same terms as we have done till now. So the algorithm here is based on the Monte Carlo Markov chain. And what I'm going to give you is a kind of naive algorithm where we are going to update the gradients in order to optimize the probability distribution, which in practice means that we are going to set the gradients to 0. We want to drive them to 0. So we would typically then, in machine learning, we would set a parameter, which we are going to call for eta, which is a learning rate. And there are, for those of you who have taken a course in machine learning, you know that there are many ways by which you can define these learning rates and optimize it, and setting up learning schedules in an iterative way where you take into account information about gradients. But so this parameter is normally called learning rate, and everything here is actually based on modifications of Newton's method, or Newton-Raphson's root searching method. Raphson's root searching method. And I'm assuming now that you are familiar with that. It's based on a simple Taylor expansion, and it's the standard default method in optimizing functions. So you need to set a learning rate. We need to set the number of Monte Carlo cycles, MC. So in this case, it's not Markov chain, but it's Monte Carlo cycles. So let's just call that for I. We don't need to set it here now. And then if we want to train a restricted Boltzmann machine, which now has only one visible layer and one hidden layer. What we will do now is to set up an iterative scheme where we simply write while not converged. And the convergence criterion here is us driving these gradients to as close as we can to 0. Or if we have some stopping criterion, that if the gradient is smaller than, let's say, a number which we have fixed, let's say 10 to the minus 6 or 10 to the minus 5, then we would stop the iterative process. We would typically then, first, we would sample a batch of events. And here you can use standard gradient descent, or you can use stochastic gradient descent, sample a batch of variables, of samples. So we are splitting down the domain of events. So when we perform a set of Monte Carlo cycles, we would generate a set of samples, and we could simply call these samples for some x1, and then x2, etc., up to some x of m. And then what we would do next, we would calculate the gradient. So compute the gradient. Which in our case is going to be the derivative of delta of this with respect to this parameter theta. And in our case, we are going to maximize we are going to calculate the gradient of the log of p of x as a function of theta, which means that implicitly here, we are already treating the hidden nodes. So then when we've done that, we have set up the sample, we initialize the gradients, and then we will have a loop now. We would loop over all the samples which we have, I equal 1 to this Monte Carlo samples which we have set to number of Monte Carlo cycles. So now we are performing the Monte Carlo cycles. Then we would have a new loop here for j equal 1 to the number of samples which we have. Then we would now perform a Gibbs update or Monte Carlo or Metropolis update. So we would now define a new set of events. So we would have an x of j, which is given by this xj's given. We are suggesting a new configuration. And then these are given by the Metropolis sampling. Metropolis, or if you're using Gibbs sampling, that's another way of doing that. So that means that we are setting up now a set of data points, and then we end here and end here. And then with these points, we actually calculate now the new gradients. So we would have a gradient. So this is going to be the gradient, G. And we have the new gradient, which now will be given by minus this previous value. And then this is multiplied with the delta, and then we have a log, and we have an epsilon here, which is this parameter which we define, no, sorry, eta. Minus eta multiplied with this, no, sorry, this is not the, I was writing the wrong line here. So we are going to optimize, we will calculate the gradients, and we are going to optimize the parameters by using the gradient. So this is contains now a plus because we are maximizing the gradients, and this should be multiplied with the gradients. Delta log of p of x of theta. And this ends the loop. And at the end, we will have the optimal parameters. So this gives or returns the optimal parameter theta after a given number of iterations. So in this specific case, what you would have now is something which really looks like the standard Monte Carlo sampling, which you have been doing till now. The problem which you end up with here, and as we discussed last time, is actually the derivative of the partition function. Because when we take this, the derivative with respect to theta of log p of x as a function of theta, this is actually given when we now write it out in terms of this function, which we can calculate. Normally, it's a multidimensional function, but it's something which we can calculate. But then we have the gradient of the partition function. So the first term, as we mentioned last time, is called the positive phase. Since we're now dealing with a maximization problem and not a minimization problem, this is the common approach in this type of generative methods. Then the problem is actually the calculation of the partition function. And we saw last time, so from the previous lecture, from last week, the way we typically calculate this, the log of the partition function, which is the difficult thing. This is actually the main difficulty in calculations of generative models. This is given by the expectation value of the log, the gradient of the log of the function which we had, this p of x, as a function of theta. So I'm not going to repeat everything here. You will also find a detailed discussion of these quantities of how you calculate this quantity log c of theta in the textbook by Goodfellow et al., which I gave you the link to, et al., and this is in chapter 18. So the calculation of the derivative of the partition function is actually one of the bottlenecks in these type of methods. And remember now that, as you have seen also in the quantum mechanical case, these are typically multidimensional functions. Now, the difference between what we are going to do and what you have in this type of generative models is that we are not going to optimize a probability, but we are actually going to optimize the trial wave function. So if we now change from a Boltzmann machine to our case, so our case, we will use a Boltzmann machine in order to define the wave function. So we are going to define the probability distribution here as before. So it's going to be given by 1e to the minus, and we are going to put the temperature equal to 1 because we're not going to use temperature as a variable. So we are simply going to rewrite this in terms of a so-called energy function, which will depend on the hidden layers and the input variables, or the visible layer. And the visible layer is actually going to be something which will define our wave function. And then we have this divided by z of theta as before. But what we are going to do now is not to optimize the probability distribution, but we are going to actually assume now that the wave function squared, so the trial wave function, which we have x as a function of the parameters theta, is now going to be given by this probability distribution, which is the marginal distribution. And just to remind you of that, px of theta, if we have a continuous function, this is going to be given by dh of p of x of h of theta. So in our case, the quantity which we want to set up is a trial wave function, which is now going to be defined by this Boltzmann distribution. Now, what you can do, in addition, since this Boltzmann distribution can be pretty agnostic to the quantum mechanical requirements you have, so there may be properties of the wave function which this will not catch, you can actually take this probability distribution and modify it and add other ansatz for the wave function. So you could think of you having something which contains the correlation part of the wave function, and then use that one to define this probability distribution together with the Boltzmann machine. So one thing we have to make sure when we are setting up this is that this Boltzmann machine gives us a wave function which respects the property symmetries. So if we are dealing with a wave function which is antisymmetric, we would like this distribution typically to be antisymmetric. Or if we are dealing with a total wave function which is symmetric, we have to make sure that the probability distribution is symmetric. Now, one way this is done if you're dealing with an antisymmetric wave function is that you would often multiply this Boltzmann distribution, which is a positive definite quantity. You would multiply that one with something like a determinant or a Slater determinant if you are dealing with fermions and have a requirement on antisymmetry. And that will make sure that the total wave function will have a symmetric part multiplied with an antisymmetric part. And then the total wave function will be antisymmetric. So there are some important considerations to think of here. Now, so in our case here, what we are going to end up with is that we are going to minimize the same quantity which we had before. So we are going to minimize the expectation value of the local energy, the same integral, as a function of these variables theta, which now is given, in our case, in terms of the expectation value, and we have an integral over d of x, and then we have a p of x, and then we have theta, and this is multiplied with the local energy, which will now depend on x, essentially only on x, so there's no dependence on this variable theta in here. And actually, the local energy depends on theta because we have the trial wave function. And this quantity here is something which we normally approximate with a sum over all the Monte Carlo cycles which we have. And then we will typically set up an E of L of xi as a function of these parameters theta. And that means that the function which we end up minimizing is exactly the same as we had in project number one. So same function. As in project number one. So that means that we need to calculate the derivative of the trial wave of the expectation value with respect to the parameters in the trial wave function. The Hamiltonian itself does not have any such dependence. Now, the thing which we are going to need now, and we are not going to focus too much on the traditional Boltzmann machine. So I just want you to keep this distinction clear, because in the slides, you will find in the beginning how you would set up all the calculational ingredients for running a calculation with a traditional Boltzmann machine or a restricted Boltzmann machine. So we are going to have one hidden layer and one visible layer. And we are going to use this training to actually produce a probability distribution, which we then can use in our case to represent the trial wave function, which then enters the optimization process of the local energy. So I hope you see these kind of differences. And I want to emphasize one thing, that is that compared both these approaches, so compared with a standard neural networks, there is no backpropagation. This is the way we typically train a neural network in a standard way, which also means that we don't use automatic differentiation. Okay, so the quantity which we now are going to optimize is then the quantity which you have seen before. So we are ending up with, so let me just bring up my notes here so I have them clear in front of me. So the quantity which we want to optimize now is the gradient of the energy. So we're going to have a gradient of the expectation value of the energy. So this is the local energy as a function of these parameters theta. And we know that this brings us, since we have many parameters theta, this brings us to a D, and I'm going to write this expectation value in the standard physicist way. So this is the expectation value of the local energy of d theta y, and that's going to be given by 2 times, and then we have the expectation value. So these are integrals over the local energy multiplied with 1 divided by psi, and then I have d psi, I should put that one, of d theta y, the variational parameters now, minus the expectation value of the local energy, which is just the energy we've been calculating before, and multiplied with this 1 divided by psi of d psi of d theta y. So this is the same quantity which we now want to optimize. And in our case, we can always rewrite this derivative of the wave function with respect to the parameters theta y. We can then just rewrite these in terms of the log. And this is very convenient for us because the wave function is going to be given in terms of exponentials. So what we will have then will be a d theta, d of psi with respect to theta y, one of these parameters. And then this is something which we can rewrite as the log, or ln of psi of d theta y. So this is the type of way in which we will normally calculate this quantity in terms of, since, as you see, the probability distribution now of a wave function psi is going to be given by the Boltzmann distribution. So that means that we have this constant z of theta, which we are coming back to, and then we have the exponential here. So in our case, just to remind you quickly of what these parameters are going to look like, we are going to have a network where we will have a set of hidden nodes. So we have a hidden node h1, h2, up to some h of n. And then we have the visible nodes. And in our case, the visible nodes are going to be represented by the number of particles times the dimensionality of the system. So we will have an x1, an x2, up to some x of n. And then we are going to have connections between the visible nodes and the hidden nodes. The restricted Boltzmann machine has, in general, only one hidden layer. You can stack more hidden layers. Then the training gets a little bit more complicated. You would have more parameters, and that obviously gives you more flexibility in the training. But in general, what we are going to have is then a connection given by weights. So this will be a weight with h x1 connecting to h of n. So there will be a weight here, there will be a weight w11, etc. And the way we are going to deal with these type of the parameterizations for this energy function in the probability distribution, px of theta, this is going to be given by some p tilde of x of theta divided by z of theta. And I just want to remind you of this px of theta, which is now going to be either an integral or a sum over d of h. And then I have e to the minus beta, and we are going to put beta, the inverse temperature, to 1. And then we have x, h, and these parameters theta. This is the definition of that quantity. Alternatively, if we have discrete values for h, this is the so-called marginal probability without the normalization constant. This will now simply be given by a sum over the values h. And typically you can now choose in this energy So this function x of h of theta is now something which we are free to choose how we want to set it up. So this is going now to contain a set of parameters. So it will run from I equal 1 up to the, and I think I used m here to indicate the visible layer. There's going to be a set of parameters ai multiplied with x of I. We're going to have a new set of parameters. So these are normally called the biases in neural network calculations. And then we're going to have a sum over the hidden nodes. And this is going to introduce a new set of parameters, which are also the biases, times h of j. So these are also biases. And then finally, we have a double sum here over I and j up to m and n. And then we have the x of I multiplied with wij and multiplied with h of j. And these are the so-called weights. So the parameters theta then, they will contain, and now I write this as a vector A, and I have a vector B, and then I have a matrix W which contains the weights. So this theta is a collective container for the parameters of the theory. And we are now going to optimize a trial wave function in the calculation of the energy. So the quantity we will optimize, which in the machine learning literature is called the cost function, is going to be this object. So that means the expectation value of the energy. And this is where we are going to reuse everything we did in project number 2. No, sorry, project number 1. And that means that the only thing we need to do then, compared with project number 1, is to change the trial wave function. And obviously, we have to pay more attention to the way we are going to do the gradient descent. So in project number 1, since we had only one parameter, we could stay with a simple gradient descent. Here, it can be convenient now to actually think of a stochastic gradient descent with an adaptive learning rate. Now, the typical number of parameters which we have, if we have 2 particles, in 2 dimensions, that means that this quantity which we defined m is equal to 4. So that means 2 particles multiplied with the dimensionality of the system, so which gives us 4 degrees of freedom. So that means we will have 4 visible nodes, x1, x2, x3, and x4, and they will represent the positions of the different particles in 2 dimensions. If you're in 3 dimensions, you would need 6. If you have 10 particles in 2 dimensions, you will need 20 input nodes, etc., etc. So what we are doing now is actually to generate a probability distribution by optimization, which now is going to represent the wave function which we have. So at the end of the optimization process, what we have is a new probability distribution, which now has been trained, and then we can simply give to it any value of x, because we have trained the probability distribution to find the optimal parameters theta here. And that means that now we can generate new positions, x1, x2, x3, etc. So you see the whole philosophy behind generative models. So you train a probability distribution so that you can generate new points. This probability distribution which you have trained can also be used to calculate or to estimate errors. So what we are going to do after the break now is to set up the gritty-nitty details which are needed. And I want you to keep in mind, before we take a small break now, the difference in philosophy between the standard generative deep learning approach, where you use, for instance, a Boltzmann distribution to set up a probability, and where you optimize the probability or the log of the probability. This is in contrast to what we are going to do, where we start with a probability distribution. This means that we have this probability distribution here, which is given by a Boltzmann machine. But what we optimize and what we define as our cost function is the expectation value of the energy. And that's the quantity we optimize. Now, there is another reason for why we do this. And this is in case you have time and you want to look at how you can implement a neural network to solve the same type of problem. Now, if you use a neural network, then you need to implement the backpropagation algorithm, and you need also to implement, let's say, automatic differentiation and other things. This is an additional complication to what you have from project number one. So I'm thinking about both time, this is a 10 credit course, and you being able to wrap up in time and do some experimentation as well. So using the Boltzmann machine is the easiest way to transit from project one to project two and look at deep learning methods. However, the Boltzmann machine, since you now are choosing a type of trial energy, so this is where you bake in your parameters, this can be less flexible than a standard neural network. And actually, the current research shows that dealing with a standard neural network gives much better results than what you can obtain with a Boltzmann machine. So if you have time and you want to explore that, that is an optional path in project number two. But my recommendation, and this is mainly due to time and the constraints which we have, and some of the constraints are, the boundary conditions are that this is a 10 credit course. The Boltzmann machines are the easiest ones to implement. If you now go back to what we said about generative models and deep generative models, the whole machinery of Boltzmann machines combined with the unsupervised learning is actually something which forms a very exciting research avenue in artificial intelligence. So all the things which you have heard about from ChatGPT and this generation of images with software like DAL-E, these are all based on generative models. So you train these models on some data. In our case, we're going to train it via the optimization of the energy. But in other cases, you would train these models, these probabilities towards data, and then you can use these to generate new data. That is the basic philosophy of generative models. And it's a very hot research field. So we are trying in a way to catch many birds with a stone. I hope you can see that basic philosophy. So one thing is to learn more about generative models. We're going to apply this to the quantum mechanical problem. But you should keep in mind that this is an extremely rich field within deep learning. And it's where we actually can think of this as one of the really big avenues for future research in deep learning. So supervised learning, where you want to fit a model to some specific data, whether this is classification or a regression case where you want to fit a function. These are very interesting cases per se, but the more interesting cases lie within the possibility to generate new data. And this is where current research in machine learning has its main emphasis. That means unsupervised learning. Okay, so I wanted to use this first hour, I went a little bit over time, to actually give you this kind of broader picture and then nail it down to the practicalities which we need to implement. So after the break, we are going to look at the practicalities which you need to program. So the focus today is on implementing these Boltzmann machines in order to optimize the energy. And this energy will now depend on the parameters of a neural network given by a restricted Boltzmann machine. I hope you can now see the wood for the trees and that the overarching motivation is a little bit clearer before we now dive into the details. So what we are going to do now is to set up the type of Boltzmann machines which we are going to use. And one of the things which we are going to use as an ansatz is the function for this energy. So in our case, we are going to define this energy ansatz to be given by, so let me just put up the expressions for it. So this will be a function of x and the hidden variables and these parameters theta. So this is just the collective container. And what we are going to assume now is the following. We are going to assume that x is a continuous variable. And that and it's going to be given by a Gaussian. So remember now that we are defining a probability distribution. So we could actually think of the probability distribution as containing now one variable, which is a continuous variable given by a Gaussian. And then we let the h be a binary variable. And we are going to let the h take values of 0 or 1. Alternatively, if you're dealing with spin systems, it would be natural to have -1 and +1. So actually, these models of the Boltzmann machines, in order to simulate quantum mechanical system, has been very much applied to so-called spin Hamiltonians. And these spin Hamiltonians are Hamiltonians like the Heisenberg model, the Ising model, and the Potts model, and other spin type of models where you take binary values, so you can have more spin variables. But the standard models often are models which deal with a given combination of Pauli X, Y, and Z matrices. Now, what we have when we take h as a binary variable, this means that the function which we are going to set up, this x of h of theta, is going to be given by a so-called Gaussian binary Boltzmann machine. A Gaussian binary restricted Boltzmann machine, RBM. So restricted because we have restricted ourselves to only one hidden layer, and we have restricted ourselves to no interactions between the nodes in the same layer. So if you look back at the drawing which we made before the break, there are actually no connections between the nodes in the same layer. So the hidden nodes, they connect only with the visible nodes. And that is pretty similar to what you have with a standard neural network. So we have one hidden layer and no connections between internal nodes. And that means that the parameters which we have then, when we set up this function of x, of h, of theta, is now going to be given by a sum over I equal 1 up to n, the number of visible nodes. And I'm going to have an x of I minus a bias parameter, a of I, which, so a of I is a parameter we need to train, divided squared. Now, this is often written in terms of the variance. But since we don't know the variance, it's common to actually put that quantity to just 1. So it's common then to just put this sigma of I equal to 1 here. And then this contains thereafter a sum over the hidden nodes. So we will then have this parameter bj multiplied with h of j, where h of j now take values 0 or 1 only. And then finally, we have now the sum, the double sum, which then links the hidden layer with the visible layer. And then we have these weight parameters. So this is going to be the energy function. Now, there are some considerations now. So one of the considerations, which is going to make life a little bit easier for us, if we look at this Gaussian binary function, this is actually something which is a positive definite function. So we can Then what we can do then, we can assume the following. So we can assume now that our trial wave function psi of t here, which depends on x and the parameters theta, that is going to be given by the Boltzmann distribution, but the square root of the Boltzmann distribution. So we're going to have 1 over the square root of the partition function. And this is going to be given then in terms of the square root of the sum. And now I'm summing away the hidden nodes, hj here. And I have my e to the minus e, and then I have my x, and I have my sums over hj, and then this is a function of the parameters theta. So we're going to treat the partition function in a somewhat sloppy way, because that's actually one of the difficult things to deal with. We're going to think of the partition function as something which is now just a constant, and we are not going to include that one in the optimization process here. Now, one of the things which we need to do when we are now setting up these expressions, you see now that this e is going to be given by the terms which you see here. So if you look at these expressions here, we now need to perform the sum over the hj's. So if we do that, what we're going to get now is the following. So I will have 1 over the square root of z, and then I'm going to have a term which is going to be given by e to the minus. So I'm just going to give you the final answer here. I will have a sum over I equal 1 up to n. And then since the summation over hj is not relevant for us, so that means that what we are going to get then is a sum over xi minus ai squared. And I'm going to put this sigma I to 1. And this is going to be multiplied with the product of j equal 1 up to the number of hidden nodes. And this is multiplied with 1, and we get 1 here because one of the variables takes the value 0. So then we are simply multiplying with 0. So the exponential of 0 just gives us 1 plus e of bj. So I'm just performing the sum here plus, and I need a little bit more space. So let me just rewrite this on the next line. So it's actually not so difficult to show this. So this is multiplied then with the product of j equal to 1 up to n. And then we have the square root of 1 plus e, and then I have a bj plus the sum over I equal 1 up to n. And then I have a x of I of wij. And then I've taken the derivative with respect to h. No, not the derivative, I've been summing over h, and h takes the value either 0 and 1. So remember now that this hj takes values 0 and 1 only. Now, if you go into the Jupyter notebook, you will see the intermediate steps. So I'm just setting up the final result here. So that means that when I go back to the calculation of my log of psi, so if we now go back to the thing which we need to compute in the expectation value, what we need to calculate is this quantity here. So that's something which we need to set up. And then finally, we need also to set up the final expression for the local energy here. So when we are setting up all these final terms, we are ending up with a set of equations which have to be programmed. So let me just bring back this. So when I now calculate my ln of the trial wave function, so since I'm assuming that this quantity is positive definite, that means that now when I take the ln of the trial wave function as a function of x and theta here, what I'm going to have then is something which is going to be given by -1/2, and then I have ln of z, and this is a quantity which I'm coming back to a little bit later. But then we get minus, and then we have a sum over I equal 1 up to n here, and then I have my xi minus a of a squared. And now it depends on whether you want to keep this term 2 sigma I squared here. If you do that, you need to bring in an additional factor over, if you want to keep that term, you have 2 sigma I squared, but then since you have a factor of 1/2, you need a 4 of sigma I squared, and it's common to actually put sigma I equal to 1, as I said, because we don't know that value. It becomes a new parameter actually. So you could tune the trial wave function with respect to a sigma which you don't know. And then we have the final term, which gives us +1/2. And now I have a sum over the hidden nodes up to n here. And that is given by ln of 1 plus e. And then I have a bj plus the sum over I equal 1 up to n. And then I have my xi of omega ij here. So this is my log of the trial wave function. So that is one of the technicalities which we need. And now when we are optimizing, we need the derivatives with respect to these parameters. Optimizing, what we would need then is a derivative of this quantity, dln psi, with respect to the parameters a of I. So if you now go back and see what we need to set up in the calculation of the gradients, let me just go slowly back here. So this is the final quantity which we are going to evaluate and set up a code for. What we need then is obviously this calculation here, which we have rewritten in terms of the ln of psi. And you see now the benefit of setting up exponentials as trial wave functions. We have the expression for the local energy. This is going to be unchanged from what we have seen before. The only thing which we need to add now is actually the expectation value of this quantity here. And then when we are taking the derivatives, we need the derivatives of the log of the trial function. And what we need then are actually the different derivatives here. So let me just set them up so we can take those expressions and calculate these derivatives. So this term here is simply going to give us 1 over 2 sigma squared. And then I'm going to get an x of I minus ai. Obviously, we get a factor of 2 when we take the derivatives. I have the derivative of the same quantity with respect to dbj. And that's going to give us 1 divided by, and then I have 2 here, and then I get the parameters of e of minus bj minus, and then I have this 1 over sigma squared, and then I get the term of I equal 1 up to n, and then I have my xi of wi, and this contains a +1 as well here. And then finally, I need to take the derivative with respect to the weights, wij, and these are the quantities which I then need in order to set up the final derivatives which enter the expectation value. So if I do that, I'm going to get the value of x of I, obviously, and then I'm going to have a 2 over sigma squared, and then I get an e to the minus bj, and then I get minus 1 over sigma squared, and it has a sum over I equal 1 up to n, and this contains xi of omega ij +1 here. So these are the derivatives which we need to put into the program. So the next thing which we need is actually our Hamiltonian. So let me see, there's a question in the chat here. So the sigma squared, if you're thinking of a Gaussian distribution, so just let me quickly, there's a question in the chat here about the Gaussian or the sigma squared, because we are taking the Gaussian binary approximation for this energy. So if you then think of a Gaussian distribution here, and if you have a distribution which depends on some mean value, mu, and then some standard deviation, this is given by e to the minus, and then you have some x minus mu squared divided by 2 over sigma squared. So the sigma here, it comes from the fact that you have chosen a Gaussian distribution for the continuous variables. Now, remember now that this is one ansatz for this energy, and you will see that that fits pretty well with the calculations which we have done in project number 1, because we have used a harmonic oscillator. And the harmonic oscillator has a part of the wave function, which now behaves like a Gaussian. It has e to the minus x squared. So that means that this kind of approximation for that energy has already in it some of the features of the wave function we are looking after. If you were to look at a situation like the hydrogen atom or helium atom or something like that, then your wave function should have an exponential behavior, but it should actually go like e to the minus x instead of e to the minus x squared. So sigma here is introduced simply because you have a Gaussian ansatz for the visible part. Now, since you don't know this sigma, you would typically normally put that one to 1. And that's what normally happens actually in the calculations, because else it would become a new parameter. But clearly, this is something you could look at when you now have a different harmonic oscillator traps. So the Gaussian binary, which we have chosen here, this ansatz here for the energy, is something which now has an element of the wave function, which we know from the harmonic oscillator. So the type of approaches you do in this energy ansatz, this is actually where you make your ansatz for the parameters you want to fit. This is something you could change with other distributions if you now have, let's say, a standard exponential distribution, which you want to have into your wave function. That's fully possible. And if you now want to include fermions, the way you would treat that is actually to multiply this ansatz from a Boltzmann distribution with a Slater determinant, because that would typically include the anti-symmetry which is needed. So I hope that answers the question which you had. So the thing we end up with a set of parameters here. The next thing which we need to deal with is actually the Hamiltonian itself. And the Hamiltonian is now given by kinetic energy. There is a harmonic oscillator type of potential. And then we can include an interaction piece, which then can contain either the Coulomb interaction, or it could be, if you wish to replace what I've suggested in project number 2 with the same system as you had in project 1, feel free to do that. Now, what we need next thus is actually the local energy, which we know is given by 1 over psi, and then we have the Hamiltonian times psi here. And in our case, this is actually given by 1 over psi, and then I have a sum over the number of particles, which I label as I, up to the number of particles, little n here, to distinguish from the uppercase n. And then I have a minus 1/2, and this is in terms of natural units. So I have the derivative, and then I have plus. In our case, we have a harmonic oscillator frequency, and this contains also the radius of the different particles. So this is the standard harmonic oscillator potential. And then I'm going to just write in a very generic term, I less than j, and then I have some interaction, which depends on the relative distance only between the particles. And this is acting on psi here. So this is going to give us, when we summarize everything, we would then have this in terms of this trial wave function, which is now given by the Boltzmann machine. And in our case, again, it will be very useful to actually rewrite this in terms of the exponential ansatz, which we had, comes from the Boltzmann function. And then we know that when we take the derivative of the trial wave function with respect to the kinetic energy, this term here, this is something which we can also rewrite in terms of the log of the trial wave function. So the only thing which changes now is the kinetic energy, which can be calculated in an efficient way in terms of the log of the function here. So if we look at the local energy, when we summarize everything here, so the local energy will now be given in terms of the following quantity. So I'm just going to give you the final answer when you plug in the wave function. And there are many of the calculation details actually given in the lecture slides. So you will have a term which goes like a function of 1/2, and then we have a sum over I equal 1 up to n. And then we need to set up the kinetic energy, which will be given by a minus. And then I have a d of ln. So it's going to contain a log of the trial wave function and the derivative with respect to the, so let's connect that one. And this is a derivative with respect to x of I. And this quantity here, the first derivative comes squared. And then I have a second derivative term, which goes like d of x of I. And this is the second derivative of ln of psi. And then I have my term, which deals with the harmonic oscillator part. So that's going to be given by omega. And now I'm going to have an Ri squared like this. Sorry, this should be another type of parenthesis here. So times this one. And finally, since I have an interaction piece, which now depends only on the, it has no operator, which changes the type of wave function. What I get then is a term which is very simple to add, which is now just given by I less than j, and then I have the interaction term of Rij. Now, this term here, which you see, is also not affected. So this should actually be an Ri squared. This term, which you see here, is also not affected by the trial wave function, because you multiply it with the wave function and divide by the wave function. So the only thing which is affected by the trial wave function is actually the calculation of the kinetic energy, which is now going to contain these two terms. So that means that you need then to set up derivatives of, since we already have the derivatives of this ln of psi, and the first derivative and the second derivative, we need now expressions for these quantities. And all these expressions are actually listed in the Jupyter notebook here. So if we go back to the Jupyter notebook, so I just wanted to list to you. So what you need now, we already have this d ln of psi with respect to dx of I. We need also the d ln of psi with respect to xi again. So this is the second derivative. So these equations here are equations which are all programmed in the or you have the final expressions in the Jupyter notebook. So see Jupyter notebook for final expression. For the final expressions. And then after this, we are going to go back to the Jupyter notebook and actually look at the code which you would need to implement. Now, what I wanted to say first now is that clearly what you see here is that setting up these Boltzmann machines comes at a price. So the price has to do with the calculation of the energy ansatz, which is included in the Boltzmann distribution. And this energy ansatz, which we now put to be given by a Gaussian binary, this is going to be okay for the harmonic oscillator case. You're going to notice that as soon as you add the interaction piece, it's not going to give us so good results as you would get with a standard variational Monte Carlo approach, as we discussed during the lectures. So if you remember back during the lectures, which led to the different elements which we need in project one, what I used as an example was a case with the 2 electrons, which is the case I put forward here in project number 2. The case of the 2 electrons was then, for a standard variational Monte Carlo calculation, contained a single particle piece, which was given by only the spatial degrees of freedom, because the spin part, being anti-symmetric, is not needed, since the Coulomb interaction does not change the spin quantum numbers. Then the correlated part was given by a so-called Jastrow factor, which contained another variational parameter. If I used all the elements which we developed for project number 1, I would get an energy which was pretty close to the exact energy, which for that specific case with a harmonic oscillator frequency equal to 1 should give us an energy of equal to 3. And the standard variational Monte Carlo brings us pretty close to that. Now, what you're going to see now when you add the interaction term is that this ansatz for the wave function given by a Boltzmann machine is not good enough. It's pretty good for the harmonic oscillator, but it's going to be clearly dependent on the way you do the gradient descent method. So this is something you should think of when you're setting up your codes. You can do a plain gradient descent as we did in project 1, because project 1 didn't require that much sophistication. We had only one variational parameter, but now you're going to get many more variational parameters, which means that you need to think of using a function which now can either do a stochastic gradient descent or does a stochastic gradient descent with momentum and some adaptive learning rates. So this is something you need to think of when you're going to make this a little bit more general, because you're going to have many more parameters, and then it can be useful actually to set up a stochastic gradient descent approach. Now, the thing which you see immediately here is that if you change the trial wave function, you would have to find the different expression for these derivatives. So if you change to, let's say, an exponential and binary, so you have a continuous visible layer, we want to have that because we know that the wave function takes a continuous set of variable x. So we would like to have a continuous distribution for the input variables, but we can still stay with a binary approximation for the hidden layer, so that the neurons in the hidden layer, they fire and whether they have a value 1, if not, they do not do anything. So the complication you get then is that you would need to set up all these derivatives depending on the type of distribution which you are going to choose. So we chose the Gaussian here because that is something which is going to be pretty close to the harmonic oscillator. So you see that the method allows us to reuse everything we did in project 1, but the price which we pay is that of less flexibility compared to a neural network. So next week, we will discuss how we could implement a neural network, a standard neural network, in the calculation of the expectation value of the energy. And that means that the optimization is going to include the same elements as we have here, which means that we are going to optimize the local energy, so this is going to define what in machine learning is called the cost function. So whether we do neural networks or we do Boltzmann machines, the quantity we want to optimize is still the same. So this is the quantity, which then depends on the parameters. And in our case now, compared with project number 1, the thetas are the parameters which are given by a neural network, whether this neural network is given by a Boltzmann machine or whether it's given by a standard neural network. Okay, so what I want to do now is actually bring back the code which we mentioned last week. And if you now go back to the Jupyter notebook, you will then see in the notebook for this week that we have a description of all the different Boltzmann machines first. But then if you now scroll down, so this is the first part, applies to generative deep learning methods without thinking of the quantum mechanical problem. And it contains several details on how you would actually construct the different probabilities and the optimization of the probability distribution. But then, if you scroll down after all these kind of mathematical details, which are more interesting if you want to dive into the theory of Boltzmann machines here, you can now move down to the quantum mechanical problem. And what you will find here are two different approaches. One where you set the trial wave function to be equal to the probability distribution. But what we are going to do is actually to set the trial distribution or the trial wave function to be equal to the square root of the Boltzmann distribution. So this is RBM, stands for restricted Boltzmann machine. So the details which you find here contain the kind of mathematical derivations which are needed when we now are going to set up the code here. So I'm not going to repeat everything. You will find the intermediate steps which leads to the expressions which I put in the slide. So the program which you find here is actually just an adaptation of what we had when we discussed project one. And I didn't give you the boson problem in project one, but I looked all the time at the 2-electron problem. So what we need to do now is to first define, so let me just scroll down here and show you the kind of setup which we need. So I'm going to have two particles and two dimensions. And that is going now to define my number of input layers, input nodes. So I'm going to have two particles and dimensionality of 2. So that gives me now a 4 input nodes. Then you can choose how many hidden nodes you want. In this case, I just put up 2 here, but you can have more. And then I'm setting up the parameters. I'm setting up the biases and the weights. And I'm simply just using a normal distribution for them. You would need to play around with that. I put a learning rate, which is pretty small. This again becomes a parameter in the theory. And then finally, I perform a brute force gradient descent. And this is not very elegant. So I calculate the derivatives with respect to A, the parameter B, the biases, and then the gradient for the weights. And then I update weights and biases by simply multiply the gradients with a learning rate. And this is a brute force implementation of gradient descent. And as I said, in project number 1, this was something we could live with easily, because in project number 1, we also had only one derivative, one variable which we vary. Here now we have many more variables. Actually, in this case, since we now are linking 4 input nodes with 2 hidden nodes, we would actually have a matrix of dimensionality 3 times 2, so we would need 6 weights. And then we have 4 biases for the input layer and 2 biases for the hidden layer. So that gives 6 plus 6, so we would have 12 parameters which need to be optimized. This is still a kind of baby case when it comes to optimization. But keep in mind now that for those of you who are familiar with more machine learning algorithms, you can then reuse what you did, let's say, in a course like FYS SDK 4155, where you set up functions for gradient descent, stochastic gradient descent, etc. So one thing which is worth playing around with is an adaptive learning rate. So here, just put it to a constant. Now, else, what you will see now is that the energy function is essentially the same as before. The energy derivatives is essentially the same as before. And in my specific case here, what I'm going to set up are clearly the different derivatives as we defined in connection with project 1. So we have the derivative of psi e, multiply that with the energy, and then we have the derivative of psi of I. So this is these are the two different terms which we have when we now need to calculate the derivatives, as discussed in project number 1. So this is exactly the same, and we have a loop over the Monte Carlo cycles, etc., etc. We have here we have importance sampling. The only thing which changes now is the calculation of these different terms. So we need now a local energy and also wave function, which is now given in terms of the Boltzmann machine. So in my case, I would have a wave function here where I also need to take into account the hidden layers. So the result which I am returning is a result now which has summed out the hidden layer. And then in the local energy, what we need to do now is simply to implement these different expressions which you see in the slides here. And with those different expressions, where we also sum over the dimensionality of the system and the number of hidden layers, which we also need to set up. Then we calculate these logs of the wave functions, which are needed for calculating the kinetic energy and the potential energy. So there's also an option here if you want to include interaction, and you will see that including the interaction doesn't give very good results here. And these different implementations here also have functions which now contains a derivative of the wave function ansatz which we have, which is needed for the calculation of the derivative of the wave function. So this is where I implement these derivatives I mentioned on the slides. And then I have finally the quantum force here. And everything is tailored now to this new type of wave function. So the main difference between what you had before and what you have now is that you need to implement a different wave function. And then we have the standard energy minimization as before. And this is with or without importance sampling. And in our case, we stay with the standard metropolis sampling, because that's the one which is most efficient for the type of calculations which we are doing. And that is metropolis samplings with importance. So, or what we normally call the metropolis Hastings sampling. So these are basically the things, the elements which we need to think of. You have the mathematical details, and when you want to implement this, I mean, the best thing is actually to look back into the notes here and then see how you calculate the different derivatives and how you could implement them in your project here. And if you wish to look at the quantum mechanical case, which we had in project 1, where you now just add more and more electrons, or in our case, that would be bosons, because I don't want to have the complication of setting up a Slater determinant, because that would quickly require much more time. So this is roughly where I will stop now when it comes to Boltzmann machines. And I hope you see the overarching philosophy behind what we are doing. So we are replacing the wave function with a probability distribution. And this probability distribution may mimic the system. If we have this Gaussian binary, we do actually have a mathematical form which is not that different from the harmonic oscillator. However, if you have another type of wave function, you would actually have to change this Gaussian binary with another type of energy expression. The thing which you will see as well is that when you add this interaction, this probability distribution is not able to capture the relevant physics which is involved with the interaction. So what you would typically do then could be to add an additional variational parameter, which now would involve just the Jastrow factor. That's one possibility. And well, the basic ingredients are these. And next week, we will look at how we can set up a neural network in order to solve the same problem. But as I said, this is something which is optional in project number 2. The Boltzmann machine part is also interesting due to the fact that you're dealing with generative methods. And this is a very active field of research nowadays, especially when it comes to new developments in artificial intelligence, where you actually want to have a probability distribution in order to generate new events. Okay, this is going to stop the lecture now. I'm going to stop the recording.